In this video, we will develop the concept of work. We're often asked in physics problems to find the speed of an object. An example of that might be something like this. You have an inclined plane. It has a certain angle. You're told that the block is up here. Maybe it initially has no speed. And the block moves to some new point, some distance down the incline. Maybe that's 5 meters. And you're asked how fast is the block going there. And the plane could be frictionless or it might not be frictionless. Now, in theory, on these problems, and that means we obviously can if we can do the mathematics, we could use Newton's laws because Newton's laws tell us everything. They're correct. So we could use Newton's laws, and that's what we did in the last chapter. However, Newton's laws don't directly find speed. They find acceleration. If you find acceleration, then in theory you could find velocity by finding the change in velocity being the area under the acceleration time graph. If that graph happens to be a very special type of graph, that is, if the acceleration is constant, then we get a set of equations called the kinematic equations. And we've worked a lot of problems with that. But that implies certain things about the nature of force. In short, it means that the problem is a relatively simple problem. If the problem is more complicated, that is, if there are forces that we don't know, if there are, because we just don't have formulas for them, or if there turn out to be that the path is more complicated, then we may not be able to apply Newton's laws approach because the acceleration time graph is complicated and we can't find the area of the curve, at least not with just a formula. We probably can approximate it using a spreadsheet or some other method. Let me show you that, this isn't, we're not really talking about complicated problems necessarily. These don't have to be something like a problem at Lockheed or NASA or something. They can be very simplistic problems. Let's take kind of like a bowl here. So there's a bowl of some sort. Not a real good bowl, but there's a bowl. And let's say that you had a block of ice up here. And you wanted to find out how fast the block of ice, if released from rest, is going down here. Now that doesn't look like it's a very complicated problem. Let's just take a look at what the free body diagrams tells us about this problem. Up here, call this point A. We have some forces on it. We have the normal force this away. And we have the weight this away. And the friction force may be up. And this is X. This is Y. So that's for point A. Let's go on down here to a little bit different point. Let's say right here. Call this B. At point B, the object has now changed its position and it has a totally different looking set of arrows. The weight is still pulling down, but the normal now has changed the direction that it's pointing. And the friction has changed the direction it's pointing. So since those forces have changed direction, now there's some variable angle here that depends, going back, what that angle is there. Because of the fact that this angle changes, then these vectors break up into different components. The acceleration vector actually is changing directions as well. And then even at the bottom, you get a third free body diagram. And here, the weight is straight up. The friction is now horizontal. And the weight's not straight up. My fault. The normal straight up. The weight, of course, is straight down. Alright, so what you see is that only the weight arrow actually stays in the same direction. Every other arrow is moving around, changing directions and adding differently. That means the force is variable, the acceleration is not constant, and you cannot apply the kinematic equations. And yet this is just an ice cube being released to slide down on an inclined bowl. Alright, not inclined plane, a bowl. And in fact, there's an infinite number of free body diagrams if you were trying to do this approach with algebra. You're going to have to figure out how to write these things in terms of this angle, and you're going to figure out how to write this path by some mathematics. They call those parametric equations. Now, they're not necessarily very trivial. They require much more advanced math than you have right now. What I'm showing you is even simple problems, because of the vector nature of forces, can be quite difficult mathematically to solve. And furthermore, even if we do this and we find velocity, like I said, we have to find the area of the curve, find velocity, and then take the magnitude to find speed. This just does not seem to be getting directly to our problem. It's getting to acceleration. Finally, some forces, while they cause acceleration, have absolutely nothing to do with the problem that we want to speak about, force. And we saw that before, central motion. If you have uniform circular motion, for instance, you have an object going around like this, and at this point it's going 10 meters per second, and over here it's going 10 meters per second, and there's a force at each point, force here, there's a force here, but while the force is causing acceleration, it is not causing the speed to change. So a force can cause acceleration, but it doesn't mean it always causes an object to change speed, which is all we care about in this part of the problem. So what we're looking for a new concept that more directly ties the application of a force to the change in speed. And this new concept is what we call work. Now, what we use in physics is not the same thing as what people use the term work in everyday life. When they mean work in everyday life, they mean applying an effort, that is, applying a force. They do not mean the same thing that we do. So they use work really to mean force, not to mean the term work that we use in physics. So you have to be careful about that. Let's see if we can't expand on this concept just a little bit more. Let's look at different forces applied to an object and see how it causes the speed to change. So in the diagram here, I have a particular force, this force, F, and I'm going to push it, say a chair. This could be a chair, it could be a toy truck, it could be a block. All right, so some object. I'm going to push that object in this direction for a certain displacement. And if this thing starts at rest and you shove a block, what you'll find out is that this block picks up speed. And it picks up more speed if you push harder. So increases, and you can find out that if you double the force, in fact, it will increase. So I shouldn't say it's proportional necessarily. That's not quite true. But it increases as F increases. To apply bigger force, shove it harder, it'll speed up more. Increases as delta X increases. Push it for a longer distance, it'll be moving faster. In the second picture, I got the same block or truck, but this time I'm going to push down on the truck as it moves across. And we're going to assume for the moment that there's no friction here. Alright. So if there's things, say, on a hockey puck, and you push down on it, then as you push down and the puck moves this way, this force is not helping it. It's trying to push it in the plane. The plane's trying to push it back. This doesn't change the speed at all. This is what was happening in a uniform circular motion. We had this force pushing perpendicular to the way we were moving, and it was causing us to turn or follow a curved path, but it wasn't changing our speed. In other words, it wasn't causing tangential acceleration. It was causing centripetal acceleration. And last example, you can have an object moving at you and you can push against that object. So as the object's trying to move across the room, you're opposing its motion by pushing the other way. What happens in this case? Well, what happens is it slows down. So what we find is that there's three things interacting in this problem. One, you have to have a force. The bigger the force, the more change you may be able to make. Second, you have to have a displacement, delta x. If you don't let the thing go anywhere, that is, if you don't push it any distance across the floor, you don't change the speed. And last, the way that you apply the force, that is how this arrow F is orientated to this arrow delta x, makes a difference. If they're in the same direction, it appears to speed up. And they're in the opposite direction, it slows down. And if they're at right angles to each other, then it doesn't change the speed of the object at all. We want to put all that together in the next video to actually give you a formula for what we call the definition of work.